This footage shows the point of view of NASA's Perseverance Mars rover during a drive on Mars. Like its predecessor Curiosity, which has been exploring a different region of Mars since 2012, Perseverance has been driving through Mars's Jezero crater, the site of an ancient lake and river system, where it has been collecting scientifically compelling rock core samples. In addition to a hefty suite of 6 science instruments, Perseverance packs more autonomous capabilities than past rovers. The rover uses an autonomous planning tool called Enhanced Autonomous Navigation, or ENAV. The software looks up to 50 feet ahead for potential hazards, then chooses a path without obstacles and tells Perseverance's wheels how to steer there. Engineers at NASA meticulously plan each day of the rover's activities on Mars. But once the rover starts driving, it's on its own and sometimes has to react to unexpected obstacles in the terrain. Past rovers could do this to some degree, but not if these obstacles were clustered near each other. They also couldn't react as far in advance, resulting in the vehicles driving slower while approaching sand pits, rocks, and ledges. In contrast, ENAV's algorithm evaluates each rover wheel independently against the elevation of terrain, trade-offs between different routes, and keep in or keep out areas marked by human operators for the path ahead. More than 90% of Perseverance's journey has relied on autonomous driving, making it possible to quickly collect a diverse range of samples. As humans go to the Moon and even Mars in the future, long-range autonomous driving will become more critical to exploring these worlds. These swirls formed in a channel northwest of a pedestal crater in Cerberus Palus, near the Martian equator. The spiral patterns are morphologically consistent with lava coils on Earth that form on the surface of active and stagnated Pahoehoe lava flows and lava lakes in Hawaii. Terrestrial lava coils range from 5 centimeters to at least 10 meters in diameter. 2 types of coils have been observed in terrestrial lava flows, each with slightly different characteristics and formation processes. The first forms along distinct shear zones between 2 blocks of crust above flowing lava. The second, larger form also develops in shear zones where wrinkles in thin congealed lava skins or molten lava exuded through ephemeral shear cracks rotate slowly. With few exceptions, terrestrial lava coil orientation is consistent with the direction of shearing, although such shears are commonly not preserved. Clockwise-in coils record right lateral shear, whereas counterclockwise-in coils record left lateral shear. This observation shows a region where signature of pyroxene was detected by the Compact Reconnaissance Imaging Spectrometer for Mars, or CRISM instrument, a spectrometer aboard the Mars Reconnaissance Orbiter. Pyroxenes are a major group of rock-forming and osilicate minerals found mostly in igneous and metamorphic rocks, and they are particularly widespread in the cratered highlands, pointing to some of the most ancient portions of the planet's crust. CRISM was used by NASA to identify locations on Mars that may have hosted water, a solvent considered important in the search for past or present life on Mars. In order to do this, CRISM has mapped the presence of minerals and chemicals that may indicate past interaction with water low temperature or hydrothermal. These materials include iron and oxides, which can be chemically altered by water, and phyllosilicates and carbonates, which form in the presence of water. All of these materials have characteristic patterns in their visible infrared reflections and were readily seen by CRISM. In addition, CRISM in the past has monitored ice and dust particulates in the Martian atmosphere to learn more about its climate and seasons. Curiosity Mars rover captured this sand-capped butte, which is estimated to be about 20 feet or 6 meters tall. The butte was left behind as surrounding rock eroded away over time, deepening the broad valley Curiosity is currently climbing through. The surrounding area includes an expanse of terrain covered in surface features called polygons. The rover has found polygons several times in the past, but never so many in one place. The polygons and their honeycomb-like textures range in size from roughly 2 to 4 inches in diameter, and the features also surround and wrap around the sides of the butte. Polygonal textures can form from a variety of conditions, including drying out of the surface, like in mud cracks, temperature cycles, compaction after being buried, or shrinkage of the sediment from loss of water or mineral changes. Scientists are currently measuring characteristics of these polygons to home in on which process formed them on Mars. These newly discovered polygons are among the many surprises Curiosity has trundled across since landing on Mars 14 years ago, on August 5, 2012. Besides sulfur crystals, shiny meteorites, and other interesting geologic features, the rover has made major discoveries about the ancient Martian environment, most importantly, that it had the water, chemistry, and nutrients to support microbial life.